everybody. So today is another explanation of a lead code uh, challenge that I can't really solve, and I have to explain this to myself. So this is about um, deleting a node deleting multiples of node in a binary tree, but it's not a binary search tree. As you can see, it's not actually about like the smaller in the left or the bigger in the right. So yeah, you can see there are quite a lot of bigger numbers in the left. So okay, yep. Okay, so I had a problem with recursion and binaries. I mean binary tree in sense of like I always try to avoid, even though in my guts is actually telling me you should use recursion. Yeah, and even like some of the solution actually mention like if there is a binary tree, always think of recursion. Yeah. So this is a reminder to me that I need to use recursion. I need to practice recursion whenever I see a binary tree or whatever tree. So okay, like for example, I try to iteratively look at each nodes and try to see if I can think of a solution without using recursion, but nope, I can't. For example, like when I'm at three, yeah, when I'm at number three and then it's a node to be deleted, then I know that I need to sever the ties between this. So I can just say like three dot left is zero. I mean it's none, three dot right is none. But the problem is with severing the ties from the back of this. Yep, from this. So like three, I mean like for six will be a new branch, and yeah, for six I can append it to the trees, and seven also I can append it to the trees, but I can't sever the ties before it because there's no like self of previous. So yeah, I'm stuck. So I'm forced to see how do I use recursion. This solution is actually from Keith Gali, where I followed his YouTube video about how he solved the code question today. I think it's around like 1.5 hour video, and this lead code is actually in the last part of his like solving a lead code problem live. So yeah, um, I've been like a big follower of Cave Galley since I learned how to code in my first month because of his useful tutorial on how to use Python pandas. So take a look at his YouTube, KeithGalli, Gali, yeah, Keith Gali. Yep. So how do we solve this problem? Okay, it's using recursion. So we start with initializing a list of trees or forests or anything you like. Then I converted this solution is not in Keep Gali, but I think it's useful to do if you want to read like make it search faster, because searching in a set is actually I think is constant time, while searching in a list is I don't know whether is it a binary search or is it I don't think it's binary. It probably search iteratively, so it's probably is a big O notation time complexity. So when you set it, I mean, you convert a list into the set, its time complexity reduced to constant time. So we start with the root. Okay, so this is our root one. So this root, it's not in the delete. So this root is actually in the delete, so we can't really append it to the tree. So we just continue. So, and currently we will put it into the queue and do like a breakfast search. So while the queue is not empty, it will pop up the first thing, which is this number one node. So if the node is in delete, then it will recursively pass its branches into the recursively back into the function. This is the trick on how to severe the ties in trees, which is passing the branches into its own how to say its own function so that it just breaks off the tie. Yeah, it's the same like the trim binary search tree previously. So yep, and so it follows by if it's node dot left, then we will pass the left side into the function. So we currently will see at the left side first. So currently we at here. So number two is not in the delete, so it will go into our tree list. So I just put it here, trees. Number two is here. And okay, it will go to the breakfast search again. And it will look at his, okay, and because it's not in the delete, so nothing will happen here. It will go to else here. So it node dot left. It will append it into the queue, in the queue. And then if it's a delete, then it will just severe the ties here. Ding ding. And if it's not dot right, then append it to the queue. The number five is appended here, and yep, number five is appended here, and yep, nothing happened for number five because the yep it's not to delete, so and there's no branches. Yeah, I mean this nine is actually belongs to four. Yeah, so no branches in at number five. So it returns the tree. So yep. So so this part currently is completed. So to five. So because just now we still have the we we queue the number four. We just now queue the number. I forgot about the number four. I just skipped to number five. Yeah, we queue the number four, and then because number four is in the delete, so it will severe ties here again. You will severe the ties at here because 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 the number four is need to be deleted. So again, it will pass into the function, and because it is not in the delete, so number eight is number eight is here, number nine is here. Why I'm adding them? Because yeah, this is here self the tree to append. So and because there's nothing else down here, so nothing else will happen. So recursive we go back to number three because it's at here no dot rise if self done delete because and currently because root is in this number three is in the delete, so this is not gonna happen. It will pop it into the breakfast search again. So because it's in delete, so the left, so it's severing the ties here again. So severing the ties here, and if we're coming to visit number six, number six is not in the delete, so we add it into the root node, I mean into the trees. And seven is also not in the delete, so seven is added here. And yeah, nothing much happened here anymore. So this is done. So the answer should be 2 to 5, 8, 9, 6, and 7, 10. Let me check here in the solution. Yeah, so I actually write a test case myself here. And 1, 2, 3, 4, 5, 6, 7, 8, 9, and then no until number 10. And the to delete is 1, 3, 4, which we show in the case just now. So, and the test results here is 2, now 5, 8, 9, 6, 7, 10, which is, it should be the correct one. 2, 5, 8, 9, 6, 7, 10. Yeah. Thank you. This time taking a long time to explain because, yeah, it's a slightly long code and a bit complicated, but it's still a nice code from Keith Galley, which I love. Thank you.